And welcome to SanfordFlipMath. This is AP Calculus, working through the Finney, Demana, Kennedy book. And we are in Chapter 7, which is our last chapter for Calculus AB. And we are working on volumes. And just a reminder that what we've been doing is looking at volume in terms of cross-section. And so we've talked a little bit about like this loaf of bread and how you can look at it like slices. And if you add it up, if you take the volume of each slice and add those up, you end up with the volume of the whole thing. Today we're going to focus in a little more specifically on looking at things like, for instance, like these washers. If I were to take a shape like, let's say, a rectangle and spin it around the x-axis, then that actually looks kind of like that. And the idea is if I take a bunch of those little circles and stack them up, a bunch of little pi r squareds times dx's, and add them up, then I will have a volume. Okay, and same idea. So we're just going to focus in on things being spun around this time, whereas last time we had different shapes. Okay, so we're going to tighten up things a little bit. So we're going to find the volume of a solid formed by rotating the square root of x. Okay, so square root of x, we're pretty comfortable with that now. Okay, going from 0 to 4. And what we're going to do is take this thing and we're going to spin it around the x-axis. And the question is, what's the volume? Okay, so imagine us taking this thing and spinning it around the x-axis. Okay, and if I take one of those slices, okay, and what I want to do is find, just like what we were doing on the last section, the last chunk, is if I can find the area of this cross section, let me not write, I was thinking area of the base, that's why I wrote a B, but let me say area, times the thickness of that thing, and we'll add it up from A to B. Well, in this case, we're going to take that area from x values from 0 to 4, and we need an expression for that area. So the area, well, the shape of this cross section is a circle. Okay, well, you're familiar with the fact that the area of that circle is pi r squared. And so now the question is, what's r? Excuse me. If I look at the r for this, the radius for this happens to be whatever the y value is. And the y value for every x can be found by just looking at the square root of x. So the area really is a equals pi times, well, the y value, or the square root of x squared. So this is just pi x. So that's area. Now again, the idea here is if I look at the area of a base, times the height in this case is the dx. So here's the area of the base times the height. And we can just kind of buzz through this. This is a fairly easy one. Okay, so the antiderivative of, well, if you prefer, you can certainly pull out that pi, and then I'll do antiderivative. Okay, so antiderivative of x is just x squared over 2. And then we have a pi coming along for the ride, and we're going to evaluate that between 0 and 4. Okay, so this is pi times 4 squared over 2 minus pi times 0 squared over 2. So this is just going to be 8 pi minus 0, so 8 pi. Okay. Probably worth noting that in the last video, we actually did this same problem, and pretty similar. Looks a little different. The verbiage felt a little different, but the process was pretty darn similar. Okay, so again, the focus here is going to be on things that come from rotating. Okay, all right. Now, one of the things you want to really kind of hone in on is the fact that, where is the mass? Where is the stuff? So in this particular case, we're talking about rotating something around the x-axis, and we were talking about this solid that's being formed. Okay, so it fills in the space around that x-axis. Okay, all right, well, let's take that same idea and we're going to spin it instead around the y-axis. Okay, so same graph, same everything. It's just instead of going around the x-axis, we're going to go around the y-axis. All right, so again, we're going to take this thing right here, and we're going to spin it around the y-axis. And what this ends up doing is it ends up looking like a little vase or a funnel or something like that. And what it ends up filling in is the inside of this thing. Okay, and all of that. Okay, so again, what you want to kind of picture is, as we're thinking about cross sections, again, they are circular cross sections. Okay, so we're going to take a slice of this thing. Okay, and again, now if the slice is going this way, then that's a dy and not a dx. Okay, so as we look at this, it's going to be dy here, and we need to be thinking y values now. Okay, well, at this point is still, again, 4, 2, but instead of going from 0 to 4 that way, we're going to be going the other way, from 0 to 2, too high. Okay, so here we go, from 0 to 2. Again, these are y values now, okay, because this is dy. And then when I go to this thing, I'm going to have, again, this is still going to be an area, the cross-section area times the thickness of dy, but that area needs to be in terms of y. Okay, so it's a function of y. All right, so let's next start. The next thing we're going to do is think about what's the radius. Okay, so this is the center of my spinning, and the radius for this particular circle will be, well, a little more than 1, but that 1 is an x value. And if I go to this top circle, the radius would be 4, but again, that's an x value. So when we're doing the area of this circle, it's going to be pi r squared, and that radius this time is going to be pi times x squared. Okay, so, well, that's great, except this is supposed to be about y. Okay, well, so what I need to do is take this equation and write it about y, or about x, so I can replace this. Okay, so right now it says y equals the square root of x, and again, if I square both sides, x equals y squared. So this integral that I wrote was the antiderivative, or integral, from 0 to 2. Well, it was of x squared dy, but instead of writing x, I'm going to write y squared. Okay, so just a clarification here. This is x. It was x squared because x was the radius of these circles. Okay, so this ends up being the antiderivative from 0 to 2 of y to the 4th dy, and at this point you should be able to take this, and I'll just kind of speed through it. Okay, so this is going to be 32 over 5 minus 0 over 5, or in other words, 32 over 5 cubic units, whatever those units are. And again, since there are no units shown, I don't really need to do those units. Okay. So the picture is critical, and we'll do a couple more examples just to clarify how critical those pictures are, because you really have to be able to see where the radius is. Okay, so just a quick little clarification. What we've been doing right now so far is disks. We are stacking up disks. Okay, so these were a bunch of circles, a bunch of solid circles that were added up, and the idea is that with a bunch of them, then you have this cylindrical kind of shape that's formed from a changing size. Okay, well, this one is going to be about a washer, and you may or may not be mechanically minded, but the idea of a washer, when you're putting together, building something, is usually you put these like over a bolt or a screw. Okay, you have a screw, and the idea is you don't want it to pull through on the end, so you put this washer on the end, or you might put one on the other end before you put the nut on there to hold the thing on. Okay, so a washer is kind of like a flat donut. It's got a hole in the middle. Okay, so why am I talking about that in this case? Okay, oh, I don't think I need to be talking about that in this case because I think I'm thinking about the next example. Well, we'll see. All right, so this is 4, this is 2. Same graph, we're just going to spin this around x equals 4 instead. And you know what? I'm going to change that example so that I can do a washer method. So I'm going to spin this instead around x equals 5. Okay. So sorry about that. We're just going to change it up, but it's at least before we did a bunch of work on it. Okay. So here's the idea. We're going to spin this around x equals 5. Now, when I spin this around x equals 5, this part is going to go all the way around there. This is 1 away, and this is 1 away. So on the other side of the rotation, it's got to be, sorry, let's scooch that over a little bit. We'll call this 6. Not that it really matters. Okay. All right, so, and this part in here is going to be hollow. It's a hole. And then this part over here is going to end up way over here. Oh, more like that. Okay, my art people are freaking out right now, probably. And the non-art people are freaking out worse. Okay, so when this spins around, this whole thing ends up being like a kind of like a bundt cake kind of thing, something like that. You know, so you have a hollow center, and then something going around the outside of it. Okay, and then so what we're going to have to do is find a volume and subtract out a volume. Okay, so the slices on this. Okay, that's in the back. Okay, so one slice is going to look like that washer that we were talking about. Okay, probably worth noting that the thickness on this slice is going to be a dy. So this needs to all be about y. Okay, so let's start kind of putting together some things. First of all, the area of a washer is really going to be pi r squared minus pi r squared. Now let's think about what that means. Okay, so here's a washer. Let's just use this washer. And here I have a big R, the big radius. So that's this area. And then if I have a small circle on the inside being subtracted away, so that's the little r. Okay, so I'm subtracting that out. Okay, so this is the hole. This is, and this guy right here is the outer part. So you have the whole area, the complete area, minus the hole that's missing on the inside. Okay. All right, so let's find the area of one of these circles. So again, the idea is going to be pi r squared minus pi r squared dy. We're going to add them up for all of the y values, and the y values in this case will go from 0 to 2. Okay, so all we have to do is write down what big R and little r are. This is all about y equals the square root of x. Now let's focus on big R first. Okay, so big R is going to be from the center of rotation all the way out, or from the center of rotation all the way back to here. Now, what's that? Probably worth noting that from here to here is x. So, and then from here all the way to here is 5. So now the question is, and I know this is getting to be a busy drawing, what is it from here to here? Well, if this end is x and the whole thing is 5, wouldn't that be 5 minus x? So this is going to be pi times 5 minus x squared minus. Okay, and you might want to just hit pause right now and kind of eyeball that thing because a lot just happened. Okay, so the whole length 5 minus the x value is 5 minus x. Okay, Now the inside radius, well, at this spot it's 1, and at this spot it's 1, and at this spot it's 1 because it's the difference between 4 and 5. So I can actually just make that 1. That's like the easy schmeezy part of this problem. Okay, so for this particular problem, that inside radius, the little r, happened to be constant. It's always just going to be 1 for this particular problem. Okay, sorry, just trying to clean things up. All right, well, at this point, I still have an issue. Worth noting that this is y, these are y values, and that is the wrong letter. All right, got to do this again. So 0 to 2, 5 minus y squared, squared. Well, 1 squared is 1 times pi. Okay, and I know this is just cruising along now. Now you have to decide what's the easiest way to do this antiderivative, this integral. Okay, I think that our life is going to be easier if we multiply this out. And remember, you can't just square 5 and square y squared. This is really 5 minus y squared times 5 minus y squared. So we're going to actually have to FOIL. I have a pi in common. I would really like to just take that out front. Okay, so this is going to be 25 minus 10y squared plus y to the 4th minus 1. Now you need to look at that and say, why is that minus 1? Okay, and I'm just really proud that I didn't miss it. Okay, one more and then we'll do an antiderivative. Okay, I know this is a long problem. Sorry, that's just how it is sometimes. All right, at last, antiderivative time. So this is still volume equals. Okay, so pi times y to the 5th over 5 minus 10 y to the 3rd over 3 plus 24 y. We're going to evaluate that from 0 to 2. Okay, and so this is now equal to, substituting the 2, this is 32 over 5. I'll just put the pi out here. Okay, and minus 2 to the 3rd is 8, so 80 over 3. Gotta love these nice numbers to work with. Plus 24 times 2 is 48. All of that minus, well, plugging 0 into all these happens to be 0. And I really want to encourage you to think about that every single time because sometimes things aren't 0 on that second part of the subtraction. Okay, and pi times, okay, let's combine all that stuff together. All right, so doing some arithmetic here, this ends up being 416 over 5. I'm sorry, over 15. So that's going to be 416 pi over 15. You can call that, if you prefer, 27.73 pi, or you could even call that 87.1268 or something like that. Okay. All right, so about 87-ish. Okay, so quick little note. What I'd like to do is summarize what just happened there. When you have a washer set up, when you have a circle cut out of a circle, a hole in the middle, what we did was pi r squared, sorry, pi big R squared minus little pi r squared, and we either did dx or dy depending on what happened, okay? Well, I just want to kind of remind you that you can factor out these pi's and make this pi from a to b, big R squared minus little r squared dx. And again, that could be dy depending on which direction you're going to go. Okay, so that's kind of a little summary kind of thing. This is going to be pretty normal to happen when you're talking about rotated volumes. And if there's no hole, then you can just ignore that part because there's nothing to subtract out. Okay, all right. I think we're going to try and squeeze in one more just because, you know, different things can happen. Okay, and so again, let me do the same graph we've been working with. Just want to do lots of different stuff with the same one because that's what can happen, okay? All right, it says this time we're rotating around y equals 3. And so y equals 3, same, this is going to be real similar. And so maybe we don't need to do this, but I'm going to at least set it up with you, and then you can take it from there. Okay, so, whoops, sorry, I did the wrong one. For me, right, there we go. Sorry, it's enclosed by, and we probably need some, we would really need a little more verbiage talking about the region between this equation and the x-axis. So just so you know that I didn't put enough information here. Otherwise, what I just drew could have happened, and that could have been correct, okay? All right, so I'm clarifying. Okay, so we're going to take this thing, and we're going to spin it, not around an axis like x-axis or y-axis, but around the line y equals 3. Okay, so this is y equals 3. This is actually a really good example to do because it's kind of the opposite of what happened the last time. Okay, so if I spin it around y equals 3, then what happens is something like that. Okay, we'll make that work. Oh, that's backwards. Take that one off. All right, let me fix it. That, and there we go. Okay, so this is what we're looking at. And what I need you to see here is the part that's solid is on the outside again, so there's a big old hole in the middle, but what's different about this one is the outside has a constant radius and the inside is what has a changing radius. And I need you to understand too that it can have both the outsides changing and the insides changing. You know, if you have something like this that's being spun around the line like this, then the inside radius is changing while the outside radius is changing also, and they'll both be about x equals something or y equals something. Okay, all right, so look at where the cross sections are, okay, and it would be something like this. Okay, so here's a vertical cross section. So we're going to be adding up a bunch of stuff with a dx. And again, the setup is the integral of pi on the outside, r squared minus r squared, d, in this case, dx. Okay, so we're going to go from 0 to 4. Put a pi on the outside, and again, you can do it separately, just pi r squared minus pi r squared. The outer radius, looking at the picture, and I'm telling you the picture is the heart of the whole thing. The outer radius, the big radius, is 3. So this is going to be 3 squared minus. And then the inner radius, well, it's got to be from this y equals 3 line, but notice it's changing. So the whole distance here is 3. This distance is y. So wouldn't this radius coming from the middle, and I know my drawing's getting busy and I'm sorry. Okay, so this is y. The whole thing is 3. Wouldn't this be 3 minus y? So that's the inner radius, 3 minus y squared. So big R squared minus little r squared. Okay, and be real careful about assuming things for subtraction. All right, really, this is it. Well, kind of. Because this is about x, so this is supposed to be about x. So sorry about that. So one more thing we're going to do here, and then we can actually start doing the antiderivative. So this is going to be 9 minus 3 minus, well, y is the square root of x, and that whole thing gets squared. Okay, I'm just going to do a little bit of simplifying here, just because that would be the easiest way to do this antiderivative. Okay, so 9 minus, and then I'm going to have to FOIL, so this is going to be, 9 minus 6 square root of x plus x. Okay, one more little step, and this is what the volume is going to be equal to. Okay, so 9 minus 9 is 0, minus a negative, so this is going to be 6 square root of x minus x, so this is going to be a minus x. Okay, so I'll do minus x here. dx. And I'm going to stop at this point and just say, you should be able to know that this is x to the 1/2 and add 1 to the exponent, divide by the new exponent, etc., and go term by term. All right, so the setup is the big deal. You still need to be able to do antiderivatives. And this is all about disks and washers. So it's really all about pi r squared dx or pi r squared dy. Okay, all right, going on, and I got to roll. Thank you, SanfordFlipMath. We're done. Bye.